Bismillahirrahmanirrahim. Assalamu alaikum. My name is Tira Najaf and my roll number is 21TE06. Today I will be discussing the topic adaptive filters of digital signal processing. And for further discussion, I will be using the book of Digital Signal Processing by Lee Tan. The contents of my presentation includes overview, which includes the introduction to adaptive filters and its basic working principle. Secondly, we have the filter types and applications, which includes the filter structures, its applications, advantages and disadvantages. Thirdly, we have the advanced insights, which includes the performance comparison and the understanding efficiency of adaptive filters. And lastly, we have the concluding summary. Overview. First, we talk about the introduction to adaptive filters. What exactly are adaptive filters? So adaptive filters are signal processing tools that automatically adjust their parameters to minimize the difference between the filtered output and the desired signal. And its basic working principle is that these filters utilize algorithms to iteratively tune their coefficients, enabling them to adapt to changing input conditions and optimize signal performance. Now, if we talk about the filter structure and applications, we have different types of adaptive filters: LMS, RLS, and NLMS. First, we talk about the least mean square LMS algorithm. So LMS algorithm is widely utilized adaptive filter algorithm in signal processing, and it's known for its simplicity and efficiency in updating filter coefficients. The recursive least square RLS algorithm is an adaptive filter algorithm that provides fast convergence and robustness by recursively updating filter coefficients based on the past data. Thirdly, if we talk about the normalized least mean squared NLMS algorithm, so this algorithm computes the filter coefficients based on the inverse of the autocorrelation matrix. Then we talk about the applications of adaptive filters. Adaptive filters are used in echo cancellation, which enhance the voice communication clarity. It's used in noise cancellation, which improves the signal quality through adaptive filtering. And lastly, it has system identification, which enhances the system modeling and performance. If we talk about the advantages and disadvantages of adaptive filters, we first discuss the advantages, which includes that adaptive filters are capable of dynamically adjusting to changing signal and noise conditions, making them ideal for non-stationary environments. Secondly, these are effective in filtering out unwanted noise and enhancing the desired signal without prior knowledge of the signal characteristics. Thirdly, it enhances the desired signals by filtering out unwanted components. And moving on to the disadvantages, firstly, we have that it has higher computational complexity and resource demands compared to fixed filters requiring more memory and processing power. Second, we have that it is a potential for slow convergence and sensitivity to parameter settings, which can lead to instability and performance degradation. Lastly, we have that its performance can depend heavily on initial conditions. Moving forward to advanced insights, we first do a performance comparison between LMS and RLS algorithms. So based on the speed of convergence, we can say that generally the LMS algorithm has faster convergence rate compared to RLS, and RLS has slower convergence due to its emphasis on fast data. And if we talk about computational complexity, we can say that LMS has lower computational complexity, which makes it suitable for real-time applications, whereas RLS algorithm has higher computational complexity but offers better performance in certain scenarios. So if we talk about the understanding of efficiency of adaptive filters, we first talk about convergence rate. Convergence rate is basically the speed at which the adaptive filter adjusts its parameter to reach a state where the error between the filter output and the desired signal is minimized. And if we talk about its impact on efficiency, we can say that the faster the convergence means that the filter quickly adapts to changing conditions, leading to more effective filtering in dynamic environments. Secondly, if we talk about the computational complexity is basically the amount of computational resources, which includes the CPU cycles, memory, etc., that is required for the filter to perform its operations. And its impact on efficiency is that if we have lower complexity, which means that it will have less computational effort and it will have faster processing times, which is very crucial for real-time applications. Moving on to the stability. Stability is basically the ability of the adaptive filter to maintain consistent performance without diverging or becoming unstable over time. And its impact on efficiency is that stability ensures that the filter can reliably adapt to changing conditions without causing performance degradation or instability. So if we conclude the whole topic, we can say that adaptive filters with their real-time adaptability and error minimization are crucial for managing dynamic signal environments. They offer precise filtering and noise reduction, making them indispensable in fields such as communications and medical signal processing. Despite their computational demands, their effectiveness in non-stationary scenarios ensures their ongoing relevance and utility. Thank you. That is all from the presentation. Now I will be moving forward to the book and will further discuss this topic. So moving forward to the book, Adaptive Filters and Application is the chapter number 9 of the book. So we have already discussed what an adaptive filter is. An adaptive filter is a digital filter that has self-adjusting characteristics, and it is capable of adjusting its filter coefficients automatically to adapt the input signal via an adaptive algorithm. So moving forward, this is the spectrum illustration for adaptive filters. And this one here is the diagram for the simplest noise canceller using a one-tap adaptive filters. This block diagram here is the simplest noise canceller, which uses one-tap adaptive filter, and it is a very basic but effective method for noise reduction in signal processing. This method, briefly, if I say, uses the method of adaptive filtering with a single coefficient, or you can say tap, to minimize the noise in a desired signal. So if we go into the details, so we can see that we have two analog to digital converters, where D is the desired signal with noise. And this signal contains both the desired signal, which is denoted by S of n, and the noise, which is denoted by n of n. And this signal aims to remove the noise component to recover the clean signal. Whereas here we can see that x of n, it is the reference noise, and it is a noise signal that we want to cancel out. It is then fed into the adaptive filter. Whereas if we talk about y of n is simply a noise estimate, and it is given by the product of omega n and x of n, where omega of n is the adaptive filter with a specific weight. Then here we have the weight update mechanism, and this adaptive filter uses algorithm, which is the least mean square, to update its weight. The weight W is adjusted according to the formula omega n plus 1 is equals to omega n plus 0.01, which is also known as mu, E n x of n. And this is the iterative process, and it aims to minimize the error signal by continuously adapting the weight. So if we want to find out the error signal, we simply subtract y of n from d of n, and then we pass it through the digital to analog signal, and then we will get a signal free of noise or any degradation. So if we talk about the working principle of this block diagram or the adaptive filter, we can say that we first initialize the adaptive filter with an initial weight. We can typically set it to 0 or any other small value. Then we filter out the noise. We had the reference noise denoted by x of n, which is multiplied by the filter weight omega to produce a noise estimate, which is denoted by y of n. Then we cancel out the noise. The noise estimate y of n is subtracted from the desired signal d of n to get the error signal. Then for the weight adaptation, the filter weight omega is updated using the error signal e of n and the reference noise x of n. The weight is adjusted to minimize the error, which corresponds to minimizing the noise in the output signal. Hence, the process is iterative, so it means that it repeats itself for each new sample, which will gradually reduce the noise in the output signal. This method has its own benefits and limitations. If we talk about the benefits, we can say that this is simple and it has fast adaptation, whereas its limitation will be that it is limited to simple noise patterns and it requires a lot of good reference signals. So moving forward, these are the signal representation of S of n, which is this original signal, x of n, which is the reference noise, corrupted signal D of n, enhanced signal E of n, and adaptive coefficient omega of n. Then we move to the basic Wiener filter theory and adaptive algorithms. So if we talk about the basic Wiener filter theory, the Wiener filter is a fundamental tool in signal processing designed for optimal signal estimation in the presence of noise, and it aims to minimize the mean squared error between the desired signal and the estimated signal, providing a balance between removing the noise and preserving the signal of interest. And as this filter seeks to estimate a signal from a noisy observation, the observation can be modeled using D of n is equals to S of n plus n of n, where S of n is the original signal and n of n is the noisy signal. And then we had the goal for minimizing the mean squared error. So we minimize the mean squared error by simply taking the square of the estimated signal. And moving forward, we have this example in which we have been given a quadratic, a mean squared signal function for the Wiener filter, and we have to find the optimal solution for omega prime to achieve the minimum MSE J minimum and determine J minimum. For this, we take the derivative of the MSE function and set it to 0 to find the value of J. There we take the derivative and find the value of omega. Then we take its derivative and we substitute the value of omega prime into the question, and we find the value of J minimum. Then we move on to the applications of we have already talked about the recursive least square algorithm and the least mean square algorithm in the presentation. So we will move forward to the applications. The applications include the noise cancellation, system modeling, and line enhancement. The noise cancellation basically means that we want to remove the unwanted noise from the signal while preserving the desired signal by adapting to the changing noise characteristics. And the working principle of this is that adaptive filters continuously adjust the filter coefficients that minimize the difference between the desired signal and the noisy signal, and it adapts in real time, which allows it to respond to changing noise environments. And if we go further in the category of noise cancellation, its applications are active noise control, speech enhancement, ECG, filtering, etc. Then we move forward to the system modeling, which is the second application of adaptive filters. System modeling is simply to estimate the characteristics or the parameters of an unknown system or the process in real time, and its working principle is that adaptive filters iteratively adjust their parameters to minimize the error between the system output and the adaptive filters output, effectively modeling the system. And its further applications will be channel equalization and system identification and echo cancellation, which we talked about in the presentation. Third application and the last application which we'll talk about is the line enhancement using line prediction. Is that line enhancement is used to enhance the specific frequency components of lines in a signal, especially when these components are changing over time. And its working principle is that the adaptive filters that we use are tuned to enhance the specific frequencies while suppressing others, and they adjust their parameters dynamically to follow time varying line components. And these filter adapts its frequency response to maintain the optimal enhancement of the desired components. And its further applications will be speech processing, seismic signal processing, and biomedical signal enhancement. And that's it from the chapter. Thank you very much.